This is Heat Transfer Lecture on Chapter 13. In this lecture, we're talking about radiation exchange between surfaces. This is sections 13.2 through 13.3.2 of your textbook. First, we want to talk about blackbody radiation exchange. This is exchange of radiation between two surfaces, let's say 1 and 2. We define it as Q1 to 2 as shown here, as radiation leaving the entire surface 1 that strikes surface 2 minus radiation leaving the entire surface 2 that strikes surface 1. So it's kind of the net radiation between the two surfaces. On a normal surface, as you can see on the top right figure in the slide, your incident radiation is going to be reflected, and then you also have some radiation from emission of your surface. So the emitted radiation and the reflected radiation together make up your radiosity. In the case of a black body surface, you are going to say that your radiosity is only emission. If you remember, a black body is the perfect absorber, which means that whatever radiation strikes the surface will be absorbed by the surface. There's no reflected radiation. So as a result, what comes off of that surface is only the result of emission from that surface. Now, if I want to talk about radiation leaving a surface, in the case of a black body, radiation leaving a surface is not reflected radiation, it's basically emission by that surface. So then I'll write radiation exchange like this. I'll say that radiation leaving surface 1 that strikes surface 2 is going to be area 1, area of my surface 1, emission from my black body 1, and then I'll have to multiply that by my view factor from 1 to 2. If you remember from last time, this is a pure geometrical feature here. It depends on the orientation of surfaces towards one another. Then you deduct from that radiation leaving the entire surface 2 that strikes surface 1. Again, that would be A2, EB2, and then you multiply that by its view factor, which is F2 to 1. We know from before that A1 F12 is equal to A2 F21. So if I replace A2 and F21 by A1 and F12 in the second relation, then I'll be able to write everything a little bit in a more simple format. Then I'll also be able to, instead of writing EB1, EB2, I can actually expand them to what they actually are. They're emission from surface 1 and emission from surface 2. Again, from a couple of lectures ago, we know that emission from surface 1, a black body, is equal to Stefan-Boltzmann constant multiplied by the temperature of that surface to the power of 4. So EB1 depends on the temperature of the surface 1, and EB2 depends on the temperature of surface 2, and that's how you get these two T1 and T2 show up. And then if I want to simplify this, I can factorize the A1, F12, and the Stefan-Boltzmann constant, and I'll get the relation as you can see here. So this, if you take a look at the right-hand side picture, this is how we say radiation from surface 1 to 2 depends on your area, depends on your view factor, depends on the temperatures of the two surfaces. So the net radiative exchange between two surfaces that happens can be approximated as the net rate at which radiation leaves surface I due to its interaction with J, or the net rate at which surface J gains radiation due to its interaction with I. So now we're looking at blackbody radiation exchange, but then when we have more than just two surfaces. So for example, you have surface I and surface J, and the same case goes. Your radiosity will be the emission from the surface because there's no reflection on blackbody for surfaces I and J. So I could basically apply the relations from the previous slide in this slide and say Qij, last slide it was 1 to 2, but now it could be 1 to 2, 1 to 3, 1 to 4, all of these different combinations. So now I say Qij is equal to Q from I to J minus Q from J to I. Then I can actually expand it and say, well, Qi to J is actually AI, Fij, EBI, and then Qji is A of the J, area of the J, the view factor of J to I, and then the emission from surface J, which becomes EBJ. everything that we're doing here is exactly the same as what we did in the previous slide. In the previous slide, it was just surface 1 and 2, but now we're suggesting that, well, this could go from 1 to any surface, or from any surface to 1 to, there could be many combinations of this relation for different surfaces. Now, same as before, in order to simplify later, I want to replace my AJ FJI with AI FIJ. We know that we can apply this rule from the view factor rules that we covered last time. So now I can write everything as QIJ is equal to AI FIJ, and then in place of my EB, or emissions from the surfaces, I replaced it with Stefan-Boltzmann constant and temperature of that surface. Again, same as the previous slide. Now I'll have Stefan-Boltzmann constant by temperature of I to the power 4 minus temperature of J to the power 4. Now what if we have, we want to calculate net radiation transfer from surface I due to exchange with all the surfaces of an enclosure. The above relations are just the radiation between two surfaces, I and one of the surfaces that it radiates to or gets radiation from. But what if you're looking at the net radiation from surface I to all the different surfaces? This is something looking like what you see in the picture on the right. For example, from surface I, you have, let's say, Q1, Q2, Q3, Q4, Q5, or I could call them Q1, 2, Q1, 3, Q1, 4, Q1, 5. That is radiation from 1 to 2, 1 to 3, 1 to 4, or the net radiation exchange between these surfaces. So in a case like this, I would be able to use the above relation, but now there will be many surfaces that my I surface sees. So then I'll have to go over all the n number of surfaces that my surface sees. In other words, I will be able to say that the total radiation going from surface 1 to all the different surfaces that I have available, total of which is going to be n, is going to be AI Fij, and J is the whatever surface you're looking at. So AI Fij, Stefan-Boltzmann constant, and Ti to the power 4 minus Tj to the power 4. If you look, there's a summation here. So if I actually want to expand this, I'll be able to say that the total radiation from surface 1 to the other surfaces is going to be, the first term is surface 1 A1 Fi1, and then Stefan-Boltzmann constant and the temperature difference. Then A1 Fi2 Stefan-Boltzmann constant and temperature difference, and then A1 F13, A1 F14, depending on how many surfaces surface 1 is radiating to, you could just add terms to this relation. And that gives you the total radiation from surface 1 to all the surfaces that it sees. But remember, this is applied for enclosures or enclosure-like environments. What do I mean by that? I mean that when you have a surface, let's say I, it has to be enclosed by other surfaces. That is, there's no open area where you're not considering. There will be many surfaces that are covering around this surface 1, and all of those together will make an enclosure or a space that is covered by all different surfaces. It has to be enclosed. You can't just have two areas and say that the total two areas, and then in between or on the sides everything is open, and say that the total radiation from 1 is all that goes to 2. No, there could be areas where there's some radiation that is going to those areas. We're going to focus more on this in an example that we'll see next.